All right, you guys, let's go ahead and get started. Today we are going to talk about this idea of acceleration. Please write this definition down so that you have it in your notes. Write this definition down. I know it doesn't mean a whole lot of anything yet, but it will.
Acceleration, rate of change of velocity, can be calculated by dividing the change in the velocity by the time it takes the change to occur.
I'm going to play that again.
Acceleration, rate of change of velocity, can be calculated by dividing the change in the velocity by the time it takes the change to occur.
I know that's not what it says. Isn't that crazy? She's going off script. Shanana is awesome like that. Okay, so here's the thing. Shanana is reading this to us, and she's adding a little bit of her own script because she's awesome like that. Siri's cousin, of course. Siri's awesome, so Shanana's awesome. And, well, Cortana's pretty sweet, but Cortana's dead, so it's kind of hard. She's a smart AI, and smart AIs only last about 7 years. If you read the book series, you would know that they slowly degrade because they get too smart, and so that they start to have malfunctions. So, what was it in the last Halo? She pretty much self-destructed? Yeah. So. I'm
not talking about Halo. I'm talking about like the Cortana.
Oh, nonsense.
Rate of change of velocity can be calculated by dividing the change in the velocity by the time it takes the change to occur.
Yep. All right. Here's the deal. There's a lot of words in this definition that we have to unpack today, and that's what the whole point of today's lesson is. Okay? Acceleration, this idea, while it makes sense to us on a simple level, when it makes sense to us on a simple level, there are implications that are going to come back into play over the course of the next several weeks. And by several weeks, I mean through to Thanksgiving. We are going to be talking about this idea of acceleration. So today's lesson is basically going to be unpacking this definition and looking at it, and then we will repeat, and we will repeat, and we will repeat. Okay? So I'm going to start. There's words here that we have to look at. Acceleration is the rate, we're going to have to unpack that word, of change of velocity. We're going to have to better understand that word. When the velocity of an object changes, the object is accelerating. And so basically what we have to look at today is, in what scenarios or situations does acceleration apply? Okay? And that seems like a fundamental, that seems like an idea. So let's go ahead and switch notes over to...
Man, look at that carpet. That is amazing carpet. I love that carpet.
Yeah, yo.
I love your friend's carpet. It's great. Man, why is there a baby on a blanket?
You're slightly odd. All right. So let's go ahead and get started here. And for some reason, it's not optimizing for all... Hang on, I know why.
Let's just not talk, Jackson, and not make yourself look really
Mr. B,
weird.
what are Sony ponies?
Good question.
They're Sonys. They like Sony. So you, Parker.
Perfect. There we go.
Parker's not a Sony.
Shh. Ladies and gentlemen, bring it back. Okay, acceleration. I wanted you to write that definition down so that we could unpack it, because I probably won't be able to go back to it here for the next 10 or 15 minutes. So this idea of acceleration, we need to talk about it. First of all, what comes to mind right off the bat? Emma said cars already, so I'm just going to put that down. Okay, brainstorm for me. What comes to mind? Parker.
When runners, they speed up and they take it off the sprint, they accelerate.
Okay, so runners, he said speed up. He used the word sprint. Okay. Not the phone company, but actual running. Ariana?
Airplanes.
Yeah, airplanes. Oh, that's a good one. That's new for today. I like it. Airplanes. I love to fly. Not everyone does. Okay. Flying is it's very fun. Jaden. Trains. Planes, trains, and automobiles, ladies and gentlemen. We've just hit all three major. Okay, so trains.
Buses.
You live in Indiana. It is the crossroads of America. Everything that man can make that can be hauled on a train goes through Indiana. I didn't know if you knew that or not. Anything that man can make, radioactive waste, radioactive materials, every type of fuel source, every type of food source, every type of car, everything that can be made by man can pretty much go through Indiana. Yeah.
Did you say me?
No. Savannah?
Horses.
Horses. Hey, this is a non-judgment zone right now. This is a brainstorming activity.
Say the Amish.
Jackson.
Gas pedals. Because when you push down on them, it goes faster.
Shh. Gas pedals. Also known as the what of a car?
Accelerator.
The accelerator.
Oh, Jackson got a big one. Good job, Jackson.
No, I said
Oh, thank you, Jackson.
Colby. G-forces. All right, so let me go ahead and
High five, Jackson.
G-force like the
Not-
hamsters?
Not the
Parker.
movie.
A tank.
okay, tanks.
Now we're getting into weird stuff.
All right, cool. Emma.
To the side of your alley.
Boats.
Bullets.
Okay.
Yeah.
Yes.
Lizards.
Lit.
How do lizards have to do with acceleration?
They speed out.
All right, stop. Hands down. Okay.
2 more.
So basically, we have these ideas about what acceleration is. And I would say that for the most part, you're a third of the way there. Okay? This is exactly what I expected. We focused primarily on these ideas, and then we named specifics, but actual concepts here would be like G-forces,
That says G4 is.
forces, speeding up. The rest of them are pretty much actual objects. Sprinting would be
That was mine.
a concept. Now, in many ways, what you have listed here is accurate. These are things: tanks, bullets, boats, accelerators, gas pedals, same thing, horses, airplanes, runners, cars, trains. These are things that accelerate.
Lizards.
That undergo, yes, that undergo acceleration. Okay. But this is only, like I said, a third of the idea. So it's very obvious to me that you know that acceleration deals with this idea, this main idea, and please write this down, of speeding up. Okay, speeding up. Let's think of other ways to describe speeding up. Okay, and I'm not going to ask for the floor to be open. I'm just going to kind of walk us through this. Speeding up could be written as faster. It could be written as starting slow. And increasing speed. What word do they use in the definition? Velocity or speed? They use the word velocity. Let's look at that for just a moment too, because that is an important distinction. They use the word velocity. What is the difference between velocity and speed? Parker?
Velocity is like what the rate of what you're going, and like speed is like how fast and the.
You're close, Parker. Velocity would require a compass. Why would a compass be important?
Direction.
The direction. The direction. Young man, do you need me? What do you need?
Our iPads aren't connected, and we need the password for the students.
You need the what? What's not connected?
Our iPads.
Your iPads.
Mrs. Panning's iPads.
Oh, right. Have her bring them to me. Okay. Velocity. Parker, you're right. Direction is important. Okay? So velocity has direction. Now, I want you to make an inference here. if the acceleration uses velocity in the definition and not speed, then acceleration is going to have to depend on what also? Direction. Direction is going to be important for acceleration as well. So the next idea that you need to kind of write down, that one, this one, is that acceleration is going to be influenced by direction. And we'll come back to that in just a little bit. So direction is important, you're right. Acceleration is going to be influenced by direction. That's true. All right, so velocity has direction. Acceleration uses velocity in its definition, not speed. Not speed, which implies that direction is going to be influential here. So let's recap. Explain to me. What is it that is important for acceleration that didn't necessarily appear in our brainstorming session? Direction. Okay? Somebody else. What is important that didn't kind of come out in our brainstorming session? What is important that's going to play a role in understanding acceleration? Anybody? Repeat. I'm literally asking you the same question over again. Ellie! Direction! Yeah, direction. Oh, man. Okay. I don't know if it'll take. Hang on.
No one has this shirt. I bet you no one has.
Okay.
I'm going to start slow and increase my speed in one direction.
Which direction is that
That
direction?
direction.
Okay.
But then you're going to do it different.
All right.
Which direction are you going? That.
There are two words that we commonly associate with acceleration. Acceleration, and that usually means speeding up. But how do we change the word slightly when we're talking about the opposite effect?
I don't know the answer.
Jackson? Deceleration. Yeah, it's not meant to be super complicated here. So we have accelerate.
How many times do you think accelerate is going to pop up in this?
Oh, a lot. The word accelerate means to, and I think we've already kind of defined this as go faster. Okay?
Speed up, because we don't use.
Go faster. So we're trying to get away from this idea of using the word speed. We want to use velocity. So I might say off to the side, velocity increase. Okay, so accelerate, go faster, velocity increase. If I were to draw a dot diagram, let's just pick an object, we'll make a dot, and I wanted to kind of show this happening in time. What would the dot pattern look like, Reagan?
The dot would keep getting farther apart.
The dots would get further apart. So they would start close, okay? So we would say maybe there's a dot, and there's a dot, and then, as Reagan said, I'll make them a little bit further apart. Okay, like so.
Should we draw that?
Yeah, you should. That's a great idea. You're gonna want to draw lots of diagrams. Diagrams are the key to this class. Okay, being able to pull out ideas and draw them and interpret the diagrams. So we'll spend lots of time drawing. So if you're a drawer and you have you want to bring colored pencils, rulers, stuff like that, you're more than welcome to do so. Because as we get further in this class, our drawings we just draw more. Okay, physics is half art.
You're not good at art, are you?
Have you
Mine
seen
not-
the things he drew last year?
like that.
Oh yeah, he is good.
Thank you, Mr. Murphy.
That's last year's information.
All right, I'll put new ones on it.
Number 2.
Okay, so this is a dot diagram, not the dot diagram, but a dot diagram to show an object that is accelerating, going faster, increasing velocity. All right, now I'm going to add some arrows as well. You should do the same. So an arrow here might be this length, and this length, and this length here, and then, of course, this one. Now, arrows indicate what? Yeah.
An increase in velocity.
An increase in velocity because arrows, the whole point of an arrow is that it points in a direction. A direction.
I thought it was a back.
When we look at arrows in this class, in physics, we give them a special name. It's a cool name. It's called a vector. A vector.
Like in Despicable Me,
A
isn't it?
vector.
It sounds like a.
Vector.
It sounds like
As he spits it.
Vector. Yeah, you got to get a good saliva mix going. Vector.
Like you're like from Ratatouille.
sounds like
That's what he sounds like.
a lion.
A lion?
A lizard with a lion connected.
Lion.
Sounds
Yeah,
like
yeah.
Jeff, Michelle's on track. No, a dinosaur.
Yo, home slice.
Yo, we
Pony.
can't get any lower.
It's pony. Oh.
True. Shh. Okay. So, ladies and gentlemen, these are velocity vectors. What can you tell me about these velocity vectors? Are they staying the same or are they changing? They're changing. Okay, I got to go even a different color here. They're changing over what? Time. Erica, thanks. All right, I'm going to unpack it again. Acceleration, going faster, velocity increase. That is one example here. Okay, our dots are getting further apart. That shows we've kind of drawn arrows as another way to represent this motion. But arrows are good at giving direction, and we know direction is important because the word velocity is used in the definition. So we see velocity vectors, basically a fancy word for arrows, and we see that it's indicating a direction. We see that also those arrows are not staying the same. They are increasing. Now that's interesting. Okay, they're changing. They're increasing. And they're doing so over time, because that's the whole point of a diagram like this. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Okay, so we see this change happening over time, not instantaneous. Not what?
Instantaneously.
Very good. All right. Now, let's look at decelerate. We've looked at accelerate. Let's look at decelerate. All right. So we're going to start fresh here, see what we can remember.
That's like a Lamborghini.
Decelerate. Now, that means to go what?
Slower.
Yeah, basically slow down. Go slower.
Increase your speed.
Good
Yeah.
job, Parker.
Parker, that means a velocity.
Decrease.
Yes.
Say it again.
Go. So you go slower. You go slower.
Okay. Oh,
Oh.
good call.
I know this one.
Good job.
You start fast and you go slower.
You don't have to start.
Yeah.
Am I breaking?
Well, technically, you have to be going a speed.
Go normal speed.
Well, you don't
What's
even
normal
have to,
speed?
Yeah.
You don't have to find a
You
higher.
also don't have a
You
reference
go
point.
from a higher.
Shh. All right, bring it back. Bring it back. All right, Parker, help me out here. I'm going to draw a dot diagram like I did in the last example. How should my dots start?
Like they don't just start like very far, but farther apart. So
Okay.
You know, like they're slowing down. If you start them too close, and you gotta put like.
Then you're right. You're right, Parker. That's exactly right. So I'm going to start them about yay far apart. That's right.
A Parker apart or a Fritz apart.
One Fritz.
30, 40, 50.
Okay, so there we go. What has happened to my dots? Hannah? Excellent. They've gotten closer together. So, like on the other diagram, I'm going to draw my velocity vectors. My velocity vectors. My velocity vectors. Or in English, arrows. Yeah.
All those are connected, so technically it's one line
Hey, yo.
that just keeps going.
This is a no judgment zone. Stop ragging on my arrows, yo.
Still judgment.
Vectors.
Well, that's technically a judgment, so.
Shh. I'll take that.
That's not a
We
judgment.
only
That's
So
an
it is-
opinion. That's an opinion.
So it is a judgment zone.
Hey,
Mr. B, you're awesome.
I know.
Not okay. Fine.
It's on his shirt. Get it right.
Now you look weirder. It's gonna be so cool.
Two kinds of people wear
All right. Now,
Called MIB.
like in our previous example, we have
Can't take these.
velocity vectors. The thing that's not going to change in this particular example is that these velocity vectors, hey, relax. That's right. Shh. Are still changing over time. That is not something that changed from accelerate to decelerate. So even though they're changing in a different way, the arrows are going from being long to short. That shows that they're starting fast and getting slower. That shows that they're all still moving in the same direction. Even though it's different motion, it's still a change over time, and therefore it's a type of acceleration. Because the acceleration definition does not specify whether you're getting faster or slower. It just says a change has to take place. Just a change. And that change has to happen as a rate, which means over time. This indicates or references the word rate. Anything that happens over time is called a rate. Anything that happens over time is called a rate. So velocity vectors, they're changing over time. That's a rate. A rate. All right, so someone read the definition back to me slowly. Okay, Emma,
Of what?
of acceleration. The very first thing I had you write down.
The rate of change of velocity.
Stop. The rate of change.
Wait, but that could also be decelerate because the decelerate is the rate of
Right.
change.
So we use the term acceleration to represent both. It won't always mean going faster. When I say the word acceleration, hey, when I say the word acceleration, I might be talking about something going slower too. I know that's where it gets slightly.
Accelerating or decelerating?
Shh,
You're accelerating.
that's where it gets slightly confusing. That's why we had to go through this. So the rate of change of velocity. The rate of change of velocity is acceleration. It doesn't matter if it's going faster or slower. And now I'm going to add in a third thing after I quiz you over this idea. Okay? On your notes, or in your notes, I want you to number 5 lines 1 through 5. 1, 2, 3, 4, 5.
1, 2, 3, and 4, and 5. Do you want space between them?
Not necessarily. You're going to just put one-word answers. Okay. 5, 4, 3, 2, 1. I don't want you to talk. I just want you to write down one of 3 words. Your choices are accelerate or acceleration, decelerate to indicate an object that is changing where the velocity is going from fast to slow, or nothing, indicating that there is no acceleration of any kind. Okay? I'm going to give you 5 scenarios, and I want you to just write one of these 3 words in one of these spaces. All right, listen carefully, because I'll read each one only once. What is happening to a football after it is thrown and it's in the air? Write one of these 3 words down.
How far in the
No questions.
Wait, but can it be both?
No. Not for our purposes today.
Right after it's done?
Yep.
Okay.
What is happening? I'll read it. I guess I'll read them twice. What is happening to a football after it is thrown and it's in the air? And I'm just looking at the motion of the football as it travels over a distance.
More of a distance like this. Just to prove you wrong.
Number 2. What is happening to a car on the highway if cruise control is set? What is happening to a car on the highway if cruise control is set? Is it accelerating, decelerating, or is it doing neither? Nothing. By nothing doesn't necessarily, I'm only referring to acceleration. So either it's accelerating, decelerating, or it's not accelerating or decelerating. Okay, that's what I mean by nothing doesn't necessarily mean that nothing is happening.
You said we could use accelerate for both. So technically, if I say accelerate when it's decelerate.
Whoa.
Accelerating, decelerating.
Whoa.
Stop accelerating the. Oh.
Reagan to me. All right, number 3. What is happening if a bullet strikes a thick metal plate? So the bullet's going along, and then at the moment it strikes the thick metal plate, what is happening to the bullet?
How would it hurt?
What is happening if a bullet strikes a thick metal plate?
You're not wearing the metal plate. Maybe you are. It doesn't specify.
All right, number 4. What is happening if an egg is dropped off a building? So you hold an egg out and you let go. What is happening? Is it accelerating, decelerating, or doing neither? Last but not least, what is happening if you were on a carousel going in circles at a constant speed? Okay, let's answer these.
I feel like I got number 1 wrong because I overthink.
All right, you throw a football, and we're looking at as it's traveling through the air. Is it accelerating, decelerating, or neither? Savannah?
Decelerating.
Correct.
Yes, I overthought it.
Now,
Do you want us to write the right answers inside?
No.
hang on a minute. What's that?
Do you want us to write
I do. I don't want you to erase your original. I want you just to cross it out and put the new one. Here's the reason why. Soon as you let go of that football, what's opposing it? Yeah.
Gravity.
Well, gravity is going to pull it towards the ground. That's true. But what else? We don't even necessarily think about it because we can't see it. Yeah, air. Air slows things down. How many of you have stuck your hand out the window before? What, you're driving down the road? What do you feel?
It depends on how you hold it. This or this.
As long as there is air, air will always resist the motion of an object. So, if there's nothing else that's propelling the ball forward, the ball will slow down. Now, while you're throwing the ball, while you're in contact with it, you are making it go faster. But that's not what I was talking about. I said after it's thrown and it's in the air, which means that it's slowing down. It's not speeding up. It can't speed up. There's nothing to allow it to speed up. There's nothing there to give it oomph. Okay?
So in space, could you throw a football forever?
Yes, in theory. Well, except that gravity would eventually take hold and cause it to go into orbit, I would imagine. All right. What is happening to a car on the highway if cruise control? Gravity is infinite. It's contained in the entire universe, no matter how small or strong.
Float in space.
You float around an object in space.
That's why all the planets are still next to the sun.
Shh. What is happening to a car on the highway, Hannah? Nothing. It's not going faster. It's not going slower. It's moving in a straight line. Okay. What is happening if a bullet strikes a thick metal plate, Savannah? It decelerates very quickly, as a matter of fact. Ladies and gentlemen, there is no such thing as an instant stop, just so you know. There's nothing that can hit something and come to an instant stop. It will decelerate rapidly over a very short period of time, but nothing can go from motion to no motion instantaneously. Okay? If I look close enough at the motion, I'll see that it happens over a period of time. It always happens over time. All right. What is happening if an egg is dropped off a building? Hannah? It's going to accelerate. It's going to speed up. Okay? And what's causing it to speed up in this situation? Yes? It's falling. What's pulling it towards the earth? Yeah, gravity is. So when you're moving with gravity, it's going to cause you to go faster. All right? And what is happening if you were on a carousel going at a constant speed? Yes? Okay. I expect most of you to have put down nothing.
Yeah!
Because you said constant speed.
You're right. I said that on purpose.
It's just then it's accelerating.
But it's stop proving us wrong.
Oh, very good.
What?
Say it again, please.
If it's constant, it doesn't change.
If the speed is constant, the speed is not changing.
That's what we all were thinking.
Exactly. That's what I wanted you to think.
Oh, wait,
Okay?
but are we wrong? What are you trying to make us do? Oh my god. You guys were like, oh my gosh.
Oh, the person is moving. Wait, no. That's
Okay.
stupid. That's wrong.
You guys were like, you guys have like your plate of food down here, and you guys were like, look at all this like hair shit, and it's all shedding down onto your food. You guys were feeling your legs.
Shh. All right, stop and listen carefully because this is probably the most complicated idea for our day, and I'm going to get through this and then I'm going to release you. Okay? All right, here's the idea, right? If you're on a carousel going with a constant speed, that means that you're moving with constant motion around the center of the carousel. However, your direction is always the direction you are facing. So let's say that we indicate speed with an arrow, a vector, and we point it in the direction that the person is facing each time. So here, if you're sitting on the carousel, you're facing that direction. But then as it turns a little bit,
Now you're facing forward.
you're still moving with the same speed, so the arrow's the same length, but you are now facing a different direction. Your perspective has changed a little bit. And here, and then here, and then here, 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 and here. The arrows indicate the direction. So what is changing here? Not speed, but velocity is changing because your what's changing each time? Your direction. The arrows are pointing in different directions. So you are actually accelerating here. Acceleration is taking place because there is a change in direction. All right. When you have that down, you may go. Thank you.
You have to like prove us wrong right before we leave. We're like, oh yeah, we're so smart, and then you instantly prove us wrong and make us feel really stupid.
All right.